Hello, and welcome to the webinar entitled Learn to Design Masonry More Effectively with RISA Software. My name is Deborah Brisbane, and we'll be going through some of the software options we have available in RISA technologies. In particular, we'll be focusing on RISA 3D and RISA Floor today, talking about how we can work with masonry wall elements. As we go forward here, let's talk a little bit about the software packages we have available. If you're not familiar with all the different software packages we have, this is gives us some of the pictures here. On the top, we can see RISA 3D is on the top right. That's one of our most popular software packages out. It's a general purpose, three-dimensional software package, multi-materials, including steel, concrete, masonry, we've got wood, and as well as cold form steel in RISA 3D. And we also have another program called RISA Floor, which I mentioned we would focus on as well today. RISA Floor is a building analysis software, so it helps you design your entire building. You lay out your building floor by floor and carry the gravity loads down your building to design all of the building elements. In RISA Floor, we designate things as gravity or lateral, and then we take the lateral elements into RISA 3D. So those two programs actually communicate. We also have another program here, RISA 2D, which is the exact same program as RISA 3D, except you're in 2 dimensions in RISA 2D. We have RISA Section. This is a section property program, which allows you to build your own section properties and bring that into RISA 3D or RISA 2D. We have RISA Base, which is a base plate program. We have RISA Foundation, which does foundation design, including mat slab design, grade beams, and footing design. And we also have a program called RISA Masonry. Let's talk a little bit about RISA Masonry in particular. So RISA Technologies has been developing leading software, structural engineering software, for over 20 years. And originally, RISA Masonry was designed for single masonry walls, lintels, and columns. And it's a standalone software package, so it's doing components. You enter in the information directly into RISA Masonry, so the loads go in, the sizes go in, and then it will design that for you. RISA Masonry actually was added directly into all of the programs of RISA that we have for building elements. So as you can see on the bottom, RISA Floor, RISA 3D, and RISA Foundation can now all handle these masonry wall elements. And adding it to the full package gives us a lot of different powerful tools, versatility, and we have now the ability to have all that in one model, seamlessly integrated. So let's talk a little bit about the actual masonry project. So why would you use RISA for masonry projects? First of all, it's flexible for design. So you can design not only one wall, but you can also design your entire structure. So we're not just doing components anymore, we're doing the entire structure. But we'll also see in RISA 3D, we still have the power to do that component by itself. And we'll take a look at an example of that. Also, we have one model for all the stages of the project. That's really important because you can do your design of your gravity system in RISA Floor and take the same model that you just built directly into RISA 3D to do the lateral system. When you're finished with the lateral system, you can take the same model, that one model, directly into RISA Foundation to do the design for both the gravity and the lateral forces for your foundation. So giving you the power of that one model means that you can just build it just once. We also have here is an automatic seismic and wind load generator for you. So as you build your building, RISA will actually calculate those loads for you for both the lateral loads for seismic and wind. We also have multiple materials available. So you can do your complete masonry design in RISA 3D and RISA Floor. But you can add in there steel moment frames, you can add in wood framing, you can add in any materials you need directly into that model, so it's not just masonry, as well as you can take that all and do your concrete foundation design right inside of RISA Foundation. So all these different materials can be done in that one model. Integration with Revit Structure for full BIM modeling. So as people develop their models, you want to be able to take the model into a modeling software, a BIM modeling software like Revit Structure. But the other power of this is that you can import your model from Revit Structure directly into RISA. So it's a full round-trip process. You can either start your model in RISA or start your model in Revit Structure. And that will be able to give you the power to design that model that you've already built in Revit Structure, so you can size up those members. Or if you're very familiar with RISA, you can send it out to Revit Structure to start your construction drawings. Also, we have the power to send it out to DXF. So if you're still not using Revit Structure and you're in AutoCAD, for example, you can save your model out as a DXF, and you'll have the full detail there for the wall and the rebar. So let's talk a little bit about the masonry wall design feature itself. Like I mentioned, you can have the ability to do the design of new walls, just a single wall there, but you can also evaluate existing walls. So you can do an as-built situation. You can do single and multiple story walls. So you can stack those walls. You can do multiple stories as one wall, one multiple height wall. You can also do parapets on that wall. You can add diaphragms into that wall. So you can add diaphragms into your entire model, rigid diaphragms, and then as a new feature we just added into release of RISA 3D 8.1, we have flexible diaphragms available to you. We have also is an iterative FEM model behind the scenes. So when we're looking here at this screen, we see that there's an actual submesh of plates happening underneath that wall. And what that gives you is the power to get the truly realistic behavior of how that wall is deflecting and what its real stiffness is based on what its geometry is there. So that right there will be one of the best things that we see as we develop this full model. We'll be able to work with that FEM model automatically, so no more drawing in your plates yourself. We have design codes available in RISA 3D and RISA Floor. We have the MSJC 05 and 06 ASD and strength design, so the most latest codes are available. But you also have some older codes available. So you have your MSJC IBC 02, IBC 03 ASD and strength, MSJC 99 IBC 00 ASD, as well as the UBC 97 ASD and strength design. So you just choose with a flip of a switch between which code you'd like to be using. As for loading, we can load the model up. We can load a single wall with point loads. We can see on the screen here on the right, we have point loads available. We have line loads along the top of the wall. We can put a line load in for a distributed load. We can do surface loads for out-of-plane wind forces. We can also do tapered area loads. So we have a wide variety of ways to load the model. Specifically for what we're going to be doing, we're going to look at the actual reinforcement that gets designed. So what you do to specify that, you're going to specify the reinforcement and spacing for both the axial out of plane and in plane. So you can have all those things that you're going to specify for each direction of loading. You have the rebar placement. We can place it in as centered, staggered, or both edges of the block. And we'll see an example of what that looks like in the next couple slides. We can also define our boundary zone width, and I'll also show you an example of what that looks like. Or else we can let RISA optimize the specifications for you. So what that means is here we can either specify directly, telling what rebar and what spacing we would like. Otherwise, the program will decide what is the best spacing and for that actual rebar for us. One of the other things is we can customize the materials for the block and grout properties. So we'll be able to tell the program specifically what weight block we're using and what grout block we're using in order to find the most optimal situation. We're going to get the best self-weight calculation based on those block and grout properties. Also, at the end of all this, we're going to get design. We really want to be able to see is what this wall looks like. How do we detail it? And what we're looking at here is a picture of what the detailed view looks like. So we're going to have an elevation view of the wall with reinforcement on it. We also get section view in plane and out of plane, showing us the reinforcement there. We're going to see that in the detail report. So we have a nice way to actually view this and see it after the fact once we design it. Lintels are also designed for us in RISA 3D and RISA Floor. So when we add an opening, every time we add an opening, a lintel gets placed above that opening. We can add one or more openings in a wall. They can be doors or windows, any size, rectangular shaped. And we've got lintels can be merged. So if we have two lintels on the same elevation, we can actually merge them. We'll see exactly here what the input of that looks like as we go into the program. But we also have here the picture of the cross-sectional detail. So it shows us exactly what we're looking at, a 16-inch block here with 3.5 inches, one number 6 bar from the bottom. So it's a really nice view of exactly what it looks like when we have that lintel designed. So we talked about you can put out-of-plane reinforcement in any different way here, centered, staggered, or both edges. And this picture here shows us the representation of that. So we see it centered and staggered and both edges, and pretty evident. Staggered is a little bit different. If we look at the example on the bottom, when we say staggered, what we're talking about is we're saying that each side here, we're going to stagger it from one side to the other. So from the one face to the other based on its spacing. And when you designate staggered, what you're going to say is you're going to say 48 inches staggered is the grout filling. So we're filling 48 inches inches between grout spacing. But we're actually on that face going to be 96 inches between each bar on that face, on the back face on this picture, for example. So it helps you maximize that spacing there. We also have a way to define the boundary zone width per region. So if we look at this picture, the boundary zone is going to be the two edges or the two boundary zones on each side of each region. So each region has a boundary zone on each side, and it's there as we apply in-plane loads, that boundary zone is going to be resisting our overturning moment. So each region will automatically get this boundary zone for you. And we'll see how to input that information in there too. So let's take a quick look at the model directly. So hang on a second here, and we'll jump right into our RISA 3D program. Okay, and what we've got here is wall in RISA 3D already entered for us. So it's just a single wall, and we'll take a quick look at what this wall is made of. So this wall has a certain material type, but let's take a look at the design rule. The wall is defined by its design rules. So if we look at the design rules in RISA 3D, if you're not familiar with this, on your data entry toolbar, and it's just right on here, design rules, and you'll see on the top here it's called masonry wall. And what this design rule is just defines exactly what the properties of this wall are. So this one is called a typical design rule. And it tells us that it's a 10-inch thick width wall. Okay, so we've got ability to do 4, 6, 8, 10, and 12 as that width. The block nominal length is designated here. The block nominal height is input in as 8 inches. We can change the steel designation as right now is a flexural steel of 60 KSI, and we have a shear steel of 60 KSI, but we can adjust those. And the self weight is calculated there based on this custom. So we have a couple choices for this. Let me click on this here and see what we've got. First of all, the first option would tell us that we could use the density entered in on the masonry material spreadsheet. And what that means is, I'm going to open up the material spreadsheet for us. And on the material spreadsheet, you have a masonry tab. And here we can tell the program that we're using concrete material. It'll tell us all the properties of that masonry material, and specifically our density that we'd be using. Okay, so that would be an actual constant density or a solid density of that. Otherwise, we can use what we call a custom. And when we use custom, that's actually going to say it's going to break it up based on the block material. Specifically, this one we picked out as 115 pounds per cubic foot, and the grout weight as 140 pounds per cubic foot. So if we use this custom material, we're going to use two different densities and base it on what we space in for that grouting. So if I say OK, we've got the design rule all set up, and I'm going to close that out. And when we assign this design rule, when we double-click on the wall, let's take a look. This is the wall panel editor. And to open up your wall panel editor, you just double-clicked on the wall. And in this wall panel editor, this gives us all the information we need for the actual wall. So we see right off the bat here, we're using that typical design rule that we had originally just looked at here, and it just echoes the information in here in kind of a grayed out format. So we can't really edit this information here, but it's here for our use, so we just remind ourselves what we were using in this wall here. But what we can do is talk about the regions in this wall. So you see we have regions R1, R2, and R3. And another word for our regions here is pier. Okay, so a lot of times people call it a design pier. What we're talking about here is a design region. Very similar word terminology. So when we look at this region of design, what I can do is double click on that and find out the properties of what's happening in that design region. And in this design region here, what I see is I can define that rebar that we saw previously in the slides. So we can define it based on the axial out of plane or the in plane. Okay, so you've got two options for putting in your rebar. Both are at two different directions. And in the axial out of plane, we can tell the program whether it's going to be partially grouted, fully grouted, or ungrouted. You can choose any different direction, any kind of grouting you need. We can tell it whether it should be reinforced or not. We can tell the program here to be what bar spacing or grout spacing we should be using. So 8 inches, we can tell it any of these different sizes. Or like I mentioned here, you can tell the program just to optimize it. So use whatever's best. Now the bar size, you're going to tell the program directly what bar size to be using. I have number 5 set up in here. I can tell the program to be placing the bar at centered. Both edges are staggered like we saw before. We can change our mortar type here from MS to N. We also have here is our cement type, Portland, okay, or we can use masonry, air, and trend. So we've got our options here for cement type. And then below that, we're going to tell the program about our in-plane loading. So we can have here vertical bars as number 6 if needed here. We've got number 6, this is going to be bars in the per cells 1 or 2. And these are all going to be within inside of our boundary zone width. And again, we can tell it to be optimized or not. So this will actually be an optimized size rather than what the program uses. Which is if we want to just do analysis, we would uncheck that if we wanted to specifically use that 16 inches. Otherwise, I'm going to tell the program to use what's best. Horizontal bar size we can change there too. We also have the ability to multiply by 1.5 for our ASC higher seismic zone. So I'm going to keep that on. We're here in California. So I'm going to say save and close. And what I recommend is that you set up one of your regions and then you say save as defaults. So if you say save as defaults, the next wall you build is going to have this very similar type of reinforcement, and then you can come in and tailor it to what you need. But I do recommend you say save as defaults after you reviewed it one time. Say save and close. And then I come back into the model here, and that's what's happening in this region 1. That's what I just defined. I can double-click on region 3 on the other side, and instead of having to do all that information again, I can just say same as region and choose region 1. And now this time, all this information gets saved and just copied off of the region 1. So I say save and close, and I'm okay from there. So also, now that I have all the regions defined here, the region 2 I can actually claim same as region 1 and go from there and say save and close. And all that region is defined. Now I can just double-click on the lintel, or underneath the lintel, I double-click right in the opening to define that lintel. Inside the lintel information, I find very similarly, I find the density. It can be the same as the wall, or I can designate a specific density for myself. I'm going to say same as wall for me. And I'm going to use a depth of 16 inches, so I can change my depth size for that lintel. The bearing distance here is 8 inches off the edge of that opening. It's going in at 8 inches as a bearing distance. I can change the longitudinal bar size. I'm going to leave it as number 6s now, but I can put number of bars in there, and I can also change how many bars are per layer. So I've got here, also I'm going to enter in the centroidal distance of the lowest layer from the bottom bar. Okay, so we'll see that actually in the detail drawing when we see how this designs. Also, we can change our stirrup size in here. So right now I'm using number 3 bars. I'm going to say save and close, and I have this all set up for my lintel. If I say OK, I come back out and take a look at the wall again. I have a spreadsheet in here. The spreadsheet does really give me just kind of the basics of what I had in here. It tells me the wall panel. It doesn't allow me to adjust these nodes in here, okay, because we are forcing you to be in a rectangular wall format. So I would want you to draw that out rather than changing this in here. But this is for your information so you can see where those nodes are. It does tell you here you can switch quickly from a masonry wall to another type of wall if you needed to, maybe a concrete general wall, but we'll leave it as a masonry. We can change our material set if we needed to quickly here. I've got thickness being 10 inches currently. That's what we chose. I can change that if I needed to quickly here. And then the other information here is my design rule. So all this is just the basics of the wall. I'm going to close that. And let's take a look at the loading we've got on this wall. So like I mentioned, there's a lot of different ways you can load this single wall. I'm going to turn on the viewing of my loading just by clicking on this button here, toggle display of loading. And I see that right now I'm showing my dead load. My dead load is just a distributed load along the top of that wall. Okay, so I don't need a member or anything like that. I can just draw in a distributed load on the top of that wall. The second type of loading I have is a live load. And the live load I have is here is just joint loads. So I just inserted some joints along that wall and put some loads on that. And I can do that along this wall just as a joint load. So maybe this would represent where maybe joists are framing in or something is actually loading it as a point load or a joint load. The next type of loading I have is called the wind load in the X direction. And if we look at this here, we can see that I just loaded this in the wind load in the X direction. I'm going to just display this load with some magnitude. I've got magnitudes on here. And I can see that I've got loading across there in the wind load in the X direction. And if we take a quick look here, we've got wind loads in the X direction. I've got distributed loads here. This is my basic load cases spreadsheet, and it shows me that I'm using distributed loads for both my dead load and my wind load in the X direction. I also want to look at my wind loads in the Z direction. Hang on, let's take a look at the wind loads in the Z direction. And that is actually is a surface load. And the surface load here, what we see in the surface load, it was added actually as a tapered surface load. So you can taper that surface load at any height along the wall. You can place it above that location. You don't have to put it at the base. Let me show you exactly what that tapered load looks like. This is a great new feature that we added in here. It allows you to start that load at any location, to go to any height along that wall, and then you can taper it so the top magnitude and the bottom magnitude can be different. So that's a really great feature here, allowing you to do some tapered area loads out of plane. So we've got all of those loads input into the basic load cases spreadsheet for us. We saw that here on the data entry toolbar. I'm going to close that, and let's take a look at the load combination spreadsheet. So I open up that on the data entry toolbar. I see the load combination spreadsheet, and I see that I'm applying all sorts of different loading, my dead loads, my live loads, my wind loads in the X and the Z direction. And I can solve a batch solution, which will run through every single combination possible. Solve it. There we go. All 18 of the combinations are solved real quick for us. And now we can see here we've got some results. And we have our results toolbar showing. So on my results toolbar, first thing let's take a look at quickly is the wall panel design. That's a spreadsheet here that kind of gives us a nice summation of what happened on this actual wall. So I'm going to open this spreadsheet up a little bit for us so we can see it better. And the first thing we see is we're looking at in-plane loading. So we see in-plane loading, wall panel 1, and we have the 3 regions that we showed here previously. I look at the combinations here. This is the unity check combined. And it's telling me that everything is under 1, which is what I'm looking for. And it looks like load combination 17 is governing for this in-plane load. So if we take a look back on that data entry toolbar, we see that the load combination 17 was a dead load plus wind load in the X direction. Okay, so that makes sense. Our wind load in the X direction was this direction, okay? So that would be our in-plane loading. So that makes sense. We've got that as the governing load combination. 17 seems to be governing for a lot of our different shear load combination 2. Here we've got 2 of them to be the load combination 17, and we're coming pretty close on some of these. Okay, so we're passing, so this is all good. If we look at the out-of-plane loading, that's our second tab here. We now see the same regions, but now we're looking at out-of-plane loading, and we do see a failure, and it turns red when that turns failures. So it kind of alerts us quickly to see that we have a failing region. Region 3 right now is failing. It's load combination 10 that's failing it, so we might want to just refresh our memories. What was load combination 10? That's wind load in the Z direction with dead load 1, factor of 1, and wind load Z, factor of 1. Okay, so that makes sense. Out of plane is failing in the 10 combination here. So we'll investigate that a little farther in the actual detail report. The shear checks look okay, out of plane. Okay, and then I've got all of my allowable information here on the right. The lintel information is the last tab that will be important to us here. We've got the lintel, and the flexural here shows us the flexural unity check is way under 1, so pretty good. The shear unity check is at 63%, so okay, still okay. And then we can see some of our allowables in here. So I'm going to close that out. We're going to look back on the results toolbar one more time, and we'll take a look at the concrete reinforcing tab. So they're right in the middle there. I'm opening that up. And let's switch over to the masonry wall tab. So this is a nice summation of exactly what reinforcement was required and what we're now designing for. So for concrete, for the horizontal bar size, it looks like there's none required. For the vertical bar size, it looks like I'm requiring 5 at number 8 as my minimums. Okay, in the center region there is just 5 at 72, so very, very big. Not a lot of things are going into that center region 2. The boundary zones here is just 2 at number 6s, 1 number 6 here required on each region. Okay, so maybe this is sort of our governing one, region 1. Now I can look at my lintel report, my reinforcement here, and I can see I require 1 number 6, and there's no stirrups being required. So this is another report that maybe what I would want to do is print this out for a summation of my information. Let's double click on the wall itself. After we have design, we get this nice picture showing us graphically what's happening in this wall. So you can actually turn things on and off in this model just by on the left side. So maybe we want to see the regions again, region 1, 2, and 3, just to refresh our memory about where they actually are being placed. We can also do is turn on some of this is turning on and off my out-of-plane reinforcement. You can see that little picture shows me out of plane. And we can also show in-plane reinforcement here. So just by turning that on and off, it shows some of the in-plane reinforcement. So it just helps you see a little bit closer on that screen of what you're looking at. Okay, you can turn your lintel on and off. Also, by the way, you can always turn on your grid, so if that we have this nice rendered view of this, but if that's getting in the way in your drawing or if you're viewing, you can turn that off there too. This button here, just like we see in a lot of the stuff we have very similar to RISA 3D interface outside of the wall panel editor. You can, if you zoom out a little bit and you get lost on the screen, you can always snap it back into the screen just with this picture, redraw full, and then you can print this current view if you need to too, or copy it and print it somewhere else. So you have all those options in here too. I'm going to say OK. And now let's get to the nitty-gritty of this actual detail report. So if I click on the detail, and I click on the wall itself, I can see the detail report here. I'm going to expand this up a little bit and see what we've got. Okay, so starting out, what we look at in this detail report is the regions, is the top thing on the left here. So we're reviewing region 1, okay, which was a big region for our model, so this might be one of our controlling regions. And we can flip the regions just by clicking to region 2 and 3, and we can switch from there just by dropping down that box. At the top here, what we see is we've got the code information. We've got the number of bars, what size bars, we've got here. We've got a number of tension bars and their effective depth. We've got the material information here. We have the geometry information here. So this is a 12-foot high wall with 8.5 length, 8.5 foot length of this wall. We've got fully grouted right now. It's going in as a fully grouted, 8-inch bar spacing, okay? And then we've got block nominal width, which is 10 inches, and we did turn on that 1.5 shear factor. Below that, so this is all information we really entered in, okay? That was stuff we entered in into the regions. Below this, we see is the envelope diagrams. So this is giving us our axial load in the entire region, and then the shear loads in that region, and then the moment in that region, shear in that region and moment in that region. We see the minimums up on the top and the maximums up on the bottom. Now this doesn't mean that this is where it took place. Like we can see this one is now axial is happening. The max is on the bottom at 0 feet. But we do see here we have a 3-foot maximum happening right here. So just where that spike looks like it's happening right there, something like that, right around there. So that's our maximums happening here. On the right, we have combined checks. We give you all the combined information here for your axial and your bending. We see shear, and then we do see axial and shear bending checks below that. Now this is only for in-plane, by the way. So this is your actual in-plane, and we see that on the top here. We're looking now at the in-plane only currently. We'll look at the out-of-plane in a second. As I scroll down, I see the design details of this section. So now I start to see things like what is the load combination that governed for the axial, what it looks like I have a very low load combination there. I've got design bending results here, so it gives me exactly what the section modulus is. It gives me all the different crack section analysis, the shear detail is, whether I was required here, so if I had shear steel area, what was required. And it says not required for us for our model. And below this is the cross-sectional detailing. So this gives us the cross-sectional detail that we saw previously in my slides I was showing you. So right now we're here, we've got one number 6 bar, total of 2 on each cell showing here for this in-plane loading. If we flip over to the out-of-plane, I can take a look at the out-of-plane here. Now this one's a little bit higher, right? We've got 95% here, so it's a little bit more controlling on this one. And we can look at, this is on top, is very similar information. Okay, so the only thing really that's changing is just information about the reinforcements, telling us the location of the reinforcements, the center, okay, and phase distance here gives us a little bit different information. But everything else really we entered into in this regions, in the region actual wall panel information. Again, we see the envelope diagrams, very similar to what we saw in a plane. We see the combined checks, axial bending and shear checks, and we scroll down a little bit. And now we see here the design details, so we can see our axial details here. We see the bending details and the shear details, and then another cross-sectional time here. We see number 5's at 8 inches on center is what we've got placed in this wall, in this cell here. So this is our out-of-plane information. We also in the same report can find our openings. So if I click over to openings, I can see here that this is our lintel report. It gives us all the information we told it about the lintels. So we're using number 6 bar for flexural steel. It calculates the dead weight and the wall weight for us, and that automatically in here. Gives us the effective depths and the effective widths, all information here. So we have all that geometry information. Gives us the envelope diagram. So just like we would see in a RISA 3D model of shear and moment, I have my shear report and my bending reports here summarized for me. So this is my code checks. And what's very important about this is that we kind of see a funny little drawing in here. And what is important is I ran all combinations. So I ran not only dead load and live load, but I ran some shear combinations or lateral combinations, so wind and seismic. And what's happening is we're running that through this lintel. And it's your choice. Typically what I would recommend is if you really were working with this lintel report, you'd probably want to just go back and choose a batch report for just the gravity loads. Otherwise, if you really did want to design your lintel for non-gravity loads, for lateral loads, you can use it like this too. But that would be where I would recommend you do. And then come down here and look at our detailed report for our bending. So we have our details. We can find all the maximum moments and the combinations that governed and what the steel was chosen. We also have here our picture or our cross-sectional detail showing below. So we have 3.5 inches from the base or the bottom to the centroid of that bar, and we have one number 6 bar in there. So that's all set up and ready to go, and you can print these off for yourself. And I'm going to close that down. And that's kind of the information here we have in our RISA 3D model. You can build just a single wall. You can build multiple walls off of this. So we are just showing one wall as a component in RISA 3D, but you can build multiple walls on top of each other. You can build this as a multiple-story wall. You can add in any sort of framing you need to in this RISA 3D model, and this will be just another element inside of that. Another piece just to mention is just to draw this wall. Previously, I drew this before this meeting here, but we can just draw new walls, and it's as quick as easy as just picking a masonry wall, saying apply, and then drawing your wall in place. So I'm going to jump back to my slide here and come back. And what we're going to do now is take a look at a full three-dimensional model. So we looked at a single wall just now, but what I'd like to talk about a little bit more is how to build a three-dimensional RISA floor model, okay, because you can do this also in RISA 3D, but RISA floor will help you build this model quick and easy, and it's geared a lot more towards a building model. So I'm going to jump back out here. I'm going to close down my RISA 3D, and I'm going to open up RISA floor for us for a second here. So if we open up RISA floor, if you're not familiar with RISA floor, it's going to look very similar to RISA 3D. Okay, the interface is very close, but just slightly different in a lot of different things here. Let's talk about what we're looking at in RISA Floor before we get started. So in RISA Floor, if we look at this model, I'm going to just set my shapes up here so we can see quickly. What we're looking at in RISA Floor, this is the interface of RISA Floor, so you see my data entry toolbar floats around, very similar to RISA 3D, and I can look at the full model here. So this is a three-dimensional model, just like you would see in RISA 3D. What we're looking at in these blue beams are my joists. If I zoom in a little bit, I can see that I have some wide flange as my girders, or in here I have my walls, my masonry wall elements. I can see I have some channels over here on the canopy area. So I have all these different elements in this one model. And what I do typically here in RISA Floor is the way I enter this in is on a floor-by-floor basis. So now we're looking at this in plan view. And what we would do is maybe lay out a grid, a project grid to help me lay this out, or I would import this from Revit Structure and start working on it from that, or import it floor by floor from DXF file format. So lots of different ways to draw this building. This is a pretty simplified building, so I just built it myself here in RISA Floor. But what we see is that the model starts out with all these names like steel joist and wide flange. And what you do is you tell the program what type of shape you want to be placed in there, and the RISA Floor will go ahead and design that based on the loads that are assigned to it. So you don't have to actually tell it to use a specific type of member. Like in RISA 3D, we tell it specifically what member to be using. This one is more we're going to be doing design all the time. So we could come in and explicitly call out what we want to use, or we let the program go ahead and design it for me, which is what I have chosen. Also, you'll note that there's several colors here. There's two colors. One is red and one is blue. So you'll note here, look, if you look around here, these are red wide flanges, and then we've got blue wide flanges. Now, the difference between these different colors is that blue is my gravity system. So whatever I designate as gravity, is part of the gravity system, is in blue. And whatever I designate as part of the lateral system is in red. So you've got the two different colors laid out. Now, the entire structure is going to get loaded for gravity no matter whether it's red or blue. So everything is going to get gravity loads applied to it. And then what we do is we take the model, just the lateral system, into RISA 3D. So just these red walls, these red wide flanges and columns around the exterior is what I'm relying on as my lateral system. That's what will go into RISA 3D. And we'll see that in a second as we do that. And what we also have here in RISA Floor is some default information placed in there automatically for us, which helps us make the model go a lot faster. So let's just quickly review what we have on this model. If I open up the floor spreadsheet, this is just a summation of what's happening on this model. Right now I have one floor. It's at elevation 12 feet. It has an area load default of roof. Okay, so right now we are loading this automatically with an area load of roof loading on that. Let's see what that means. So when I open up my area load definitions on my data entry toolbar, I have something called roof, and that's going to be placed on the entire structure. 10 pounds of dead load, what we call post, which is post-composite, okay, because we're allowed to do composite beams in here in RISA Floor. We have pre-composite loads and post-composite loads. My system is not composite, so I'm putting it in the post-composite dead load. We also have here live load. We have 80 pounds of live load. So I have 80 pounds per square foot placed on there. I have a reducible live load in there. You can change this live load type to be non-reducible, reducible, live load special, roof live loads, snow loads, or rain loads. You can choose any of those options in here. You can do vibration loading, so because we can check vibrations on the steel members there. And then the dynamic load is that last entry. And dynamic load is any load above and beyond the superimposed load here. So, any superimposed dead loads. So above and beyond the self-weight of the members that are going to be part of the dynamic system. Okay, so when we calculate your dynamic loads, that's what we're going to be putting. So right now we have 30 pounds there, pounds per square foot for my dynamic loading. So if I close that down, and I look here, now back on this main floor spreadsheet. That was my roof loads that were going to be placed on the entire structure. I have a default deck that gets placed on that structure. So with that default deck, there's some properties in there. Let me take a quick look at the deck information. We have metal deck in there. So this first page here just really tells the program information about concrete, but at the right here it tells us what the maximum span can be. It also tells us here the unbraced length of that deck. So right now we're using a 2-foot unbraced length for that metal deck. If I was using composite, this would be my composite information, but I'm not, so I'm going to go straight to the Loads tab. And this metal deck automatically assigns 3 pounds per square foot for its self-weight everywhere where it's applied, and then I have a construction live load everywhere where it's applied there of 20 pounds per square foot. So I have all of that placed on the model automatically. Now it has a direction or a deck angle automatically placed on that deck. So let's take a look at what that means. If I look at my plot options and show my deck, I'm going to show how this is applied. Right now I have 90 degrees applied for that deck. So automatically all these joists are being applied. The load attribution is going 90 degrees to this, which is perpendicular to the steel joists. So they're being loaded for me. If I scroll down and look at here, I also placed an additional deck on top of the channels in the opposite direction. And so this is going in 0 degrees, which means that these channels will be loaded perpendicular to their to 0 degrees here. So you've got that all set up for you. So you've got all the deck in place. So I'm going to turn the deck off so we don't have to see that anymore. And it's got all of my loads on my model, my deck on my model. Everything is all automatically placed on there. I have some load combinations created for me, dead loads and live loads. I can use the LC generator to create a couple more ASD load combinations for me. I'm going to turn off some of these and just turn off and generate some of the live loads and live load specials. And I can solve the model. So when I solve the model, all of those loading that I had automatically gets placed on the model, and each one of my members gets designed. So we're looking at all the different pieces of the model are now designed. We've got we can look at whatever maybe are some of these cantilevers. My 16 by 36 beam here is a cantilever over that column, and I can look at the detail report here and take a quick look at what this looks like. So we can see what this is. We see that we've got all sorts of point loads on this. We've got some area loads out here, applying another point load on the edge since that beam is framing in at the end. I've got all sorts of things happening on this beam itself. I see this is my detail report. If you're not familiar with RISA floor detail report, this is what it looks like here. You've got your area loads on it. You've got your shear described here. We've got moment. This is a deflection on this actual. We can see this looks a lot like a cantilever deflecting on our model here. Below that, if I had any axial loads, because it was a sloped member, I'd have that replied here or actually reported here. We estimate what loads got placed on this according to its distributed loads as well as its point loads to make sure that we could be able to track those down. If there's any live load reduction, which it looks like we did have a little bit of live load reduction placed on here, we can see that here. What the design rules are. So right now we're going to be doing design rules based on our deflection criteria. Okay, so we'll see what we go down below that. We can take a look at the deflection. Shear will be reported here, so in 19.5 capacity, and it tells us where. The bending is 98.2 capacity, so really great for that. Deflection is 65.6% of capacity, and then the reactions there. It gives us the reactions for that one. We also have our vibration analysis at the way bottom. So this is basically your beam or your joist. You can find a similar thing on your joist information. So that's your detail report. You can also, let's take a look at the detail report of what a wall looks like. Let's open one of these walls first before we just see. This is the wall we're looking at here. Let's take a look what region. Maybe region 4 would be something that would be, let's get rid of some of that reinforcement. Region 4 would be something we'd be interested in looking at. So this is a wall with 2 openings. If I click on the detail report and I click on that wall, I can see here that this wall gives me very similar information to what we saw in RISA 3D. Okay, so you see all the criteria, the materials, and the geometry. What you don't see is any of that, the shear, the lateral, and the bending information, because we're just looking at the axial information here. So maybe if we look at region 4, We see we do have some axial information in here. We've got a maximum of 3.7 kips running through that kip per foot. Note, this is a kip per foot, so we've got all that load coming in from that 1 point load there. But we've got combined checks showing me here still under capacity on this combined check for just axial. We're using number 5s at 48 inches on center. Okay, so you've got all this information, but we just ran gravity here. Okay, so what we really want to do is go check this wall for lateral, since we designated it part of our lateral system. So I've got all my gravity design in here. We can take a quick look at the forces, just the gravity forces here and the wall forces spreadsheet. It gives me, for these walls, I can find the maximum base reactions in here based on which combination. It tells me the load combination 2 was governing. And then it breaks it into dead loads, specifically dead loads for me. I'm going to scroll this down so you can see. So you've got dead loads broken out. You have pre-composite dead loads as well, and then it will give us self-weight. The other piece of that is going to be your self-weight. And then you've got your floor live loads, and it tells us which part was reduced. So you have unreduced versus reduced, all the information that you've got in there. If you had roof live loads, that would be listed in here for us too, and we could have all that broken out for us. So you have the wall forces in here. You also have wall results. So in here it tells us the information based on the region, just like we saw in RISA 3D, axial unity check, okay, but we're not seeing the bending and the shear in here. We can get the lintel information here. It tells us the lintel flexural check and the shear unity check, okay, so we've got that information for our lintels, and we're set. And then lastly we have here is our concrete reinforcing spreadsheet, where I can look at what reinforcement was designed just for my gravity system. So my gravity system here just gives us our vertical bars and our boundaries bars, and then we get our flexural steel for our lintels. So this might be where you want to really do your lintel design here in RISA floor. This would be a very good spot to do that, since we're just considering gravity. If I move over and using the director button at the top, so basically we're finished with our gravity design. Everything is done. I'm ready to consider my lateral information. So I go up to the top on the right-hand corner, I have the director button, and I click on the RISA 3D button, and it takes me into my wind load generator. So this is a great way to enter in quickly all your wind code information. We have a lot of different codes to pick from. Okay, so you've got your ASE 7s, you've got your Mexicans, your Canadian code, all that. You tell it the category, occupancy category. I'm going to choose 2. I have 110. It calculates the loads for me automatically. And what we see below is I have a wind load generation input here. It gives us basically a summation of what happened up here. I have tells me exactly which category factors are being used, the gust factors, tells us the heights, and all the information here. And then what gets calculated is going to give us all of the KZ, the height, the width, the length of the building. And then really good calculation value here is my QZ. And the one that I'm really important here is the X value and the Z value. This is the force in the X direction and the force in the Z direction. Now we assumed a rigid diaphragm for that model. So we'll see that this X force is going to be placed in our model and our Z force is going to be placed in our model based on that diaphragm, that rigid diaphragm. And we'll see that in just a second. But we probably want to take this, print it, and have it for our records so we can take a look at that separately. Say OK. The same thing happens here. We automatically generate the seismic loads for you. So the ASE 705 is calculated, picked from this drop-down list. I've got that all here. And I can see that I've got all of that. And I'm going to be able to take a quick look here at all the CT values. Okay, we've got our CT values here. Excuse me for the interruption. CT value 0.35. I've got my R value, so I may want to set up something more like my R value. I've got my SD1, SDS, and S1 listed out, and this is going to be based on my ASE 705 calculations. So I'll pick that out right off of this. I don't think this is a typical here. I think this is somewhere maybe in the East Coast here. I'm not sure, but we've got here below this, we've got CT. It will calculate here all the information based on what I've given it above. So it'll calculate the period. Here we have method A, and then we have an upper limit, and then it tells us what was used for that period. It tells us the base shear and the equation that was used from that. Okay, so we have a governing equation. If I scroll below that, it gives me the weight of this floor or diaphragm. Tells me the force in the X and the Z direction. So just like we saw forces in the X and the Z directions for our wind, we're seeing very similar for our seismic. And then we're also going to be getting calculations for our eccentricity. We're going to actually be placing this in based on eccentricity values too. So we want to get plus and minus and how big this actual diaphragm width and length is. We'll see that in a second. So if I say OK, I pop up out into the RISA 3D model. Okay, so when you see in RISA 3D, what this looks like is really exactly what it looked like in RISA 3D when we built it separately by RISA 3D. But what's nice about when you come in from RISA 4, all the loading is done for you automatically. And none of those gravity members are in here, which may make you nervous at first. You may look at this and say, don't I need those gravity members? Because that first time I looked at this model, I was sort of a little weary that I didn't have those gravity members. But what's nice is that you can see this, is that all the members come in, all the loading that was attributed from those members comes and is actually being placed on the members around there. So the walls, the columns, the beams, all of these have those loads, dead loads, live loads that were actually coming right from the RISA 4 model, just the members themselves are not there. So if we look at a little closer on the dead load and I zoom in a little bit, I can see there's point loads coming in where those things were framing in. In particular, we had a girder over here that was framing right into this wall, and I can see that that point load is right there for me. Okay, so none of those loads get lost. They're still in the model, just not bogged down with a lot of extra members. Okay, so beyond the dead loads and the live loads, we also have a lot of different loads. Let me open up my basic load cases spreadsheet and take a look. We've got, first of all, we've got wind load in the X direction. The little 1 here designates this. I'm going to click on this and open this. I see 1 point load in there for that. I have wind loads in the Z direction. I have a point load added in there. I have partial wind loads. I have earthquake loads in the X and the Z direction. I have earthquake loads with eccentricity. So all these different loads are calculated and applied into my model. And what I can do is I can actually view them in my model. So let me go and take a look at what this looks like. So wind load in the X direction is being applied directly right into the middle of that model. It's applied right into the middle of the diaphragm. So I'm going to show the diaphragm for a second here. Let's take a look at the outline. You can recognize my diaphragm from my channels. Remember that little overhang I had here? That's the diaphragm being drawn in. And that wind load is being applied right into that diaphragm. So that load gets distributed based on the stiffness of the members around it. So if we look at here, we can see that right there it's being placed right into the center there. If I look at this and we look at this back in isometric view, when I look at it in partial wind, in either direction, you can see it goes to either side of that diaphragm. This is based on my rigid diaphragm. Had I been using a flexible diaphragm, those loads would be applied directly in there as well, but what would happen then when we solve the model with a flexible diaphragm, those loads would be attributed back to the elements that would resist it. So they would actually be broken into the tributary areas of where they would be resisting. So we would see that 8 kips being broken out into the side walls here on either side, and if we were looking at in the directions of the Z, we would be looking at those being applied, that 9 kips being distributed to both sides based on a flexible diaphragm theory. Okay, so we've got all of these wind loads already placed in our model, and now we can do is we can run the model. Okay, one of the things when in data, we look back on this data entry toolbar, we look at the load combination spreadsheets, and we do very similarly, we have all these different load combinations. This time we might add in all these partials and these earthquakes, and I'm going to solve a batch solution of this one. It's going to run through every single wall on this one. Oh, it's going to give me a little warning message. I need to do the P delta analysis. I will go ahead and fill this block and tell it to do P delta. So I'm going to say yes, do all my P delta for me, and solve the batch one more time. And here we can take a look. I'm going to say take a look back at this model, and we can see what the results are on this model. So we quickly again would take a look at our wall panel design and see if there's any walls that are failing in this model. So I can scroll in here and take a look on My in-plane loads looks like everything looks to be okay underneath 1. My shear unity checks looks to be okay in here. Out of plane, I get combined checks in here without any problems. And then my shear unity checks in here. My lintel design, again, no problems in here. And what I might look in again is going back into my detail report, maybe looking specifically at a wall in particular and seeing what the detail report gives me to tell me how this is being designed. We maybe want to look at that R4 on this big wall. We saw that was kind of the bigger one in the middle with that point load. Maybe this is what's contributing to this wall. And we could go through and specifically print out these detail reports for both in-plane and out of plane. So we have all this information here listed out, and we can go through each wall and take a look at this detail report. One of the nice things in this model, too, is that we automatically are doing, like I mentioned, an FEA solution behind the scenes for you. So by doing the FEA solution, you can control your mesh of your wall and turn the global parameters on it up here at the top, and I'm going to say solution, and I can see here that right now my wall mesh is sizing to 12 inches for the maximum wall mesh for that submesh of plates inside of each wall. And I can see that submesh of plates just by going to my plot options under panels. I can say show the mesh, and it's going to show me what each wall looked like and how it got meshed. So on the general wall here on the left, I'm just going to show kind of what this looks like. It's pretty easy and pretty regular. But when we start adding openings to this wall, we start to see how this mesh can get sort of complicated. And what it's really going to do is it's going to start meshing around the openings we add in and the loads that get added into this wall. So this is the great and the powerful part of this model, is showing us how this model gets actually loaded. So, and how it gets actually analyzed. You can show things like your mesh, but you can also go ahead and look closer at your model at your contours, for example. This is another thing that you might want to take a look at how things were contoured, making sure you understand how your model is moving and how the loads are being transferred throughout the contours. We can see on the right here how these are actually being contoured. For this FX direction, XY actually is what I'm showing. What also we can do is we can go back to our wireframe view, maybe take our mesh off. We can take a look at the deflected diagram. So we solved for a couple different combinations, and we can see how this deflection, maybe we'll give it kind of an amped up deflection of maybe 400 times magnification. So we really see how this is deflecting. And we see how the beams are kind of pushing out, and as we apply, this is the deflection results for low combination 12. Let's show what that is. So we're actually pushing on this, and we see a lot of this is 400 times magnification, so a really, really large deflection. But we also see how this out of plane pushes on this wall, okay? So things like that get shown on this type of a deflection type of criteria. So showing this is really the power of having this one model, this big, big model. Rather than just looking at this as a component, we really get to see how the model behaves together. And that's really where RISA 3D becomes the most powerful way to do your masonry building as a building, not as a component. So let's go back. We can, at this point, we can look at our design results, and we can take a quick look and see if we're failing any of our design results. As we look down here, this is for our hot rolled steel, and we can see if any of these beams actually fail, and we can do is actually just highlight that, unity check, and say sort it. I'm going to say sort it by absolute max to min. So it looks like all of the beams I have right now are actually passing. But if I had any failures, that's where I might solve this model again with a suggested shape if there was a failure in here based on the lateral system. I'm going to close that. So assuming that everything works out well here in the RISA 3D model, I can use my director button to go back to RISA floor. And I can save the model, and at this point maybe go into construction drawings by exporting it directly out into DXF format, or I can send it into Revit structure, or I can just start creating actual reports based on that. So back to our slideshow here, I just want to show a couple more things talking about the load attribution inside of RISA floor. In particular, we're talking about how RISA floor distributes the loads because we are taking the loads down vertically, like gravity loads. So we automatically calculate a lot of things into those loads. like we calculate the line loads, point loads, and self-weight for you. And we can see from this picture here that we have the height of the wall with the distributed load and the point load calculated in there. And each region will get, in that region, we'll get an applied load, which will get the distributed load times its width, plus the P, which is that point load, plus the self-weight of that region. And it will also get portions of the weight above and below that opening automatically placed in there for you. Now, if you're in RISA 3D, you'd be applying these loads yourself manually, and they would be running through the FEA, the finite element analysis behind the scenes, or the actual plate model. So it would be distributed just slightly different, but very close to what this region looks like here. We also have something here in RISA floor. When we apply loads in RISA floor, we follow the rules here of 45 degrees as crossing that element. So if we look at this lintel, when we apply loads to this 45 degrees basically above the floor level, arching will not be considered. So when we have distributed loads will be applied to the lintel, we have this format here where this 45 degrees goes above that floor level. We will be distributing those loads directly to that lintel, and the self-weight of the region will be applied directly into that lintel. Okay, but when you have the actual 45 degrees not crossing the floor level, so when you can see that picture, that triangle is just slightly below that floor level, arching will be considered. Okay, and this distributed loads will not be carried across, will not be applied to the lintel. It will be just actually shed kind of to the sides, to the regions to the sides. And then you'll see that you only use the self-weight of the triangle. That 45-degree triangle will be inside that lintel. Now, again, this is just for RISA floor. RISA 3D is going to be carrying this based on the plate elements behind that. So RISA floor is going to be taking it down directly, and RISA 3D is going to be doing it on the plate elements. We've got here point loads in RISA floor are always going to be assumed to be 60 degrees. So you can see that picture here as we apply one kip, it gets applied here and distributed along that lintel in 60 degrees. So final things to talk about with RISA floor and RISA 3D and RISA foundation, the three programs we've been focusing on here. We've got the multi-material buildings is what gives us the power in this system. So you can build masonry shear walls with wood and steel floors, with roof framing. Can be wood, steel. You can use cold form as well. You can use moment frames. So when you have a garage or a storefront opening that you need extra strength for, instead of having to do that outside of the program where you have to manually figure out what those loads are going to be, you can do that inside of one model. And you can design all of those and see how they actually transfer loads based on their stiffness. And you can see how the deflection criteria, how deflection will actually work, and things like that in that one model. We also have the BIM modeling and Revit structure. So one of the things RISA is very proud of is we have one of the most comprehensive links to the Revit structure out there. We're constantly improving our link between the two programs, and we are always up to date with what we've got with Revit structure's version. And so one of the power is that you have that one model, not be it RISA 3D, RISA floor, and RISA foundation, but now you can take this one model and directly send it into your design drawings. So you can send it round trip. You can start in, like I mentioned, you can start in Revit structure, or you can start in RISA, whatever happens to be your workflow, and you can send the information back and forth. So you can update your model. One of the power of that is that everybody knows projects don't stay the same. They're always going to change. And making those changes and having to start a brand new model is so difficult and time consuming. So being able to make quick changes on one model and sending it directly to the other model really, really speeds up your process too. So we have a really, really great link between the two, Revit structure and us and RISA programs. Also, RISA allows you to design your entire building with one model. I've said that several times, but it's so important. And all that means to you is less time modeling. And what that means is more money in your pocket. We don't want your life to be spent modeling. We want your life to be spent making money. So it's really important that we make that fast and easy. And the easiest ways to do that are by making it one model, very user-friendly, and allowing you access into different programs so you can communicate back and forth. So I thank you for your time, and if you have any questions, please feel free to contact us directly at info@risatech.com. That's info@risatech.com, RISATECH.com. masonry.com. Also, please visit our website for more information on our Masonry features, as well as all of our other programs. You can download demonstration versions for as well, and please also stay tuned for more webinar opportunities. Thank you for your time.